My name is Ken Pugh, and I am the president and director of research at Haskins Laboratories, which is an independent interdisciplinary research lab that focuses very broadly on understanding the biology of human communication in all its forms, whether it is how we produce and perceive speech, whether it's how we produce or perceive written language, sign language, all variations, but we try to understand the biologic basis and the brain basis of how people develop language and literacy and what can go wrong in those who struggle with language and or literacy. We are formally affiliated with Yale University and with the University of Connecticut. I also hold faculty appointments both at the University of Connecticut and Yale University. And my area of research is a field that has been referred to as cognitive neuroscience, which is kind of the fusion of cognitive science or cognitive psychology, which studies how information is processed and the kinds of computational models of how people process information, and neuroscience. And I specifically work with studying the development of language and reading and how it may go awry in children who struggle with either spoken or written language difficulties, but I do so using a variety of tools. One of them that I use quite heavily is brain imaging techniques, particularly something called functional MRI, which is a way of using an MRI system to identify the location of circuits in the brain that are involved in language and memory and attention and reading. But we use other kinds of imaging as well, electrophysiology and other complementary modes, to try to understand how the brain creates circuits to perform language and literacy tasks. We also look at gene-brain cognitive relationships. In other words, how these differences that we observe in brain and in cognitive performance are ultimately linked to underlying genetic variation. And all of this is done here at Haskins and through our collaborations in other countries to try to develop a general understanding of how the brain learns and masters language, both in its spoken and written form, how it goes awry in populations of children and adults who struggle with language and literacy problems. And we also do a lot of work that compares these things in different written languages around the world that have very different forms to identify those underlying brain principles that are universal to all languages and those that might be different from one to another. Dyslexic children are by definition struggling with literate language, with reading, and that we find that the most frequently observed problem is that the children fail to develop efficient and automatic decoding for words. So ultimately, a skilled reader who is able to not have to think too much about the individual words and can pay attention to the story and to sort of the message of the story. Ultimately, decoding words, recognizing words, needs to be extremely fast and automatic. In fact, when we measure different kinds of brain signals with EEG and other tools, we find that skilled adult readers who do not struggle with literacy are able to recognize a word that appears in front of them visually in about 200 milliseconds. And 1,000 milliseconds is 1 second, so 200 is real fast. And if you can decode fast and efficiently, then you can process the story meaning and really extract meaning from text. So most children with dyslexia have problems in decoding, wherein we see very slow, very labored and non-automatic, and often error-prone problems of misreading. And all of this kind of creates what we think of as a bottleneck, something that limits the ability to fluently read connected text. So this is what we know by definition dyslexic, specific reading disability or developmental dyslexia presents with. what underlies it? How do those children differ? What are the cognitive abilities that we can observe even before they go to school that would predict whether reading and creating this automatic, fast decoding, whether that's going to be problematic or not? What are the underlying cognitive problems? And the strongest evidence basis for an underlying deficit in dyslexia is problems in phonologic processing or operating on the characteristics of the spoken language. This includes what are called something called phonologic awareness, which is a kind of a meta-linguistic or meta-cognitive understanding prior to learning to read, that spoken words can be broken into smaller units and that you can then learn to represent those units by letters in the case of an alphabetic language. This is a precondition. You need to be aware of the sound structure of the language in order to learn what we call the alphabetic principle, which is the link between how letters are spelled and how they relate to specific phonemes or syllables. So phonologic awareness is an important problem and a major difference in how children with dyslexia compare with others. Other aspects of phonology include phonological working memory, and this just means the ability to hold and process phonologic language information. We often see that can be a difficulty as well. But again, those are both language problems that ultimately impact the visual learning of reading. We also find in research that problems in speed and fluency in language, rapid automatized naming, for example, is another feature that seems to be very much associated with risk for reading problems. So the dyslexic, by definition, is by definition somebody who struggles with reading but is otherwise intelligent, normal, and capable of doing other cognitive skills just fine. So ultimately, it's a bit of a mystery why some children who have normal intelligence, who have adequate early opportunities to learn and stimulation, who have reasonably well-informed instruction on how to learn to decode and read, will still struggle inordinately and intensely with this ability to routinize and become automatic at printed word recognition. So again, we know from looking at these children, both as they're learning to read and also in preschool, and asking what predicts this, that the ability for the brain to operate on language is important. And that also has implications for how we think about what should be going on in a preschool environment if we want literacy to develop normally. For example, there's no indication that we should be trying to teach reading in preschool. It's not necessary. But we want to prepare the brain to learn to read. And this means reinforcing and strengthening language skills, phonological skills, appreciation of the sound structures, talking to kids a lot, the kind of thing that your grandmother would know. Interact, communicate, stimulate development of talking and listening skills and of these meta-linguistic understandings that you can, for example, facilitate by having children play rhyming games and understanding that words relate to one another in their parts. All of these things are very important in preparing the child and the child's brain to learn to read. When we try to dig more deeply into the underlying causes of dyslexia and these phonological difficulties that seem to present almost universally, we use brain research to try to get a wedge into understanding where in the brain's circuits some of these fragile or noisy processes are occurring. And this can give us a kind of insight into some children whose reading difficulties are, in fact, brain-based, and others who might be reading poorly but are reading poorly due to a variety of other environmental reasons. So therefore, in my laboratory, we do longitudinal developmental studies using multimodal, which means different kinds of brain imaging, to try to identify the pathways that allow reading to develop fluently. Our work over the years has addressed really three broad questions in the first phase. The first question is, how does the brain develop a circuit that supports fluent and efficient reading? Which components need to hook up and connect in order to allow fluent automatic decoding, that is, recognizing words in a couple hundred milliseconds, which is crucial. Our work has suggested that there are certain pathways in the left hemisphere, in some regions that are closer to the temporoparietal regions toward the top, and other important regions that are toward the ventral, which means the lower part of the left hemisphere. These regions are really critical for connecting visual codes and language information and then learning to become an automatic reader. So we've been able over the years to see developmentally what needs to happen in terms of brain circuits or connections to allow people to become automatic fluent readers. And that information has been looked at not only in English, but in many of the world's languages. Some of our research involves comparing English to Spanish, to Chinese, to other languages, to see how the brain solves the puzzle of learning to connect visual symbols to language. The second area that we've focused on, of course, relevant to dyslexia, is how do these circuits differ in children who present with specific reading disability. And the work over the years has shown in many labs, including ours, that there is a kind of a failure to organize some of these left hemisphere connective systems that link the visual areas and the language areas. And we see a kind of a lack of signal. We see problems in what's called connectivity, which is the degree that one piece of the brain is communicating with the other efficiently. We see problems in noise and in instability of signal. So we see that some of these connections in the left hemisphere that support fluent readings are problematic, and that we often see that dyslexic readers, in the absence of treatment, will try to use a different kinds of circuit. So many of these children end up using the right hemisphere more. They end up using the frontal lobe more. This is simply a description at present. We know what skilled reading looks like in terms of circuit, and we know what dyslexic reading looks like in terms of circuit. But we at least have a model then on where some of the brain differences might be that will help us understand more deeply why dyslexia happens. So the third part of our initial work was, in many ways, what you'd think of as the $64,000 question, the question that's most important to educators and parents. Not how does the brain differ when reading goes well or reading goes poorly, but are those brain differences ameliorable? Can they be changed with good remediation, with good learning opportunities? In other words, this goes to the question that is often referred to as the question of brain plasticity. The brain is plasticity, when thought about in terms of brain, is a good thing. It is the ability of the brain to reorganize, to accommodate, to give new specificity to different circuits with learning experience. So the question for some of our research, and many other labs as well, has been to look at, given the differences in the circuits that I just mentioned between good and poor readers, if you give struggling readers evidence-based, intensive, practiced experience that it can improve phonological skills, orthographic phonologic connections, vocabulary, and all of the other things that are important in building the circuit, can you see a change and a normalization in those brain circuits? And indeed, in our studies done at Yale in collaboration with Benita Blackman and with Ben and Sally Shaywitz, these studies indicated that when treatment in very young children was evidence-based and effective, that those children who responded show a high degree of normalization of those left hemisphere circuits. So in the first 10, 15 years of work in this, using brain lens into why some children struggle, we've been able to accomplish some things. We've been able to see the circuits that skill reading depends on. We've been able to see how those go differently in dyslexia, and we have preliminary evidence from many labs, including ours, that good treatment and remediation can modify or modulate some of those differences. So this is all a kind of an important first step. However, even this is not getting us where we need to go to really understand why some children struggle. Let me illustrate. If you're typically developing, you develop these left hemisphere connections. And if you're atypically developing, you don't. But that doesn't tell us why. And in order to understand why, we need to go dig more deeply into the way brains get built, the gene, brain structure, neurochemistry, and other factors that are all measurable at this point in science to help us understand why circuits form differently in different groups. The more we understand about these deeper mechanisms, the more we are likely to be able to tailor the environment to the needs of the brain going forward. And equally importantly, the more we understand about how brain development underlies the difficulties in building appropriate circuits, the more we might be able to identify those differences early in development. Because all of us would rather be in the business of prevention of reading problems rather than remediation. And in order to do so, we need to be able to identify risk long before it presents as failure. So the focus of the cognitive neuroscience these days is to understand more deeply the biologic mechanisms and pathways that underlie these problems in building circuits, that in turn underlie phonological difficulties, that in turn make it difficult to become fluent readers. And so there's many disciplines, psychology, linguistics, genetics, computer science, mathematics, communication disorders, education, all trying to come up with a better and more theoretically powerful account of what are called gene, brain, behavior connections in reading disabilities. So right now, this is a time of great discovery. It's also important to note that we are in many ways still in kindergarten when it comes to understanding the human brain. We shouldn't be so cocky about what we know and what we don't know, because the brain is an extraordinarily complex device, nonlinear systems, information processing machine par excellence. And we have only just begun to penetrate some of the principles. We have a long way to go. But the more deeply we go into these mechanisms, the more we can begin to understand why some kids need different experiences than other kids. And so ultimately, most of this is toward brain-based education. One other important thing that I think parents and teachers should be aware of is that there are often people understanding the importance of brain-based education who are jumping the gun and who claim that they have an approach to education that is brain-based. It's important that the parent and the teacher become skeptical and become careful in reading the science, in not allowing it to be overstated or oversold. Because the real science of understanding gene-brain behavior pathways in dyslexia is in a fairly early stage. We've had a lot of important discoveries. We know which areas are important so we can target them, but we really still have a long way to go. So it's very important, I think, for teachers and parents to become familiar with all these things I'm talking about without becoming neuroscientists, so that they can become both informed and, extremely importantly, skeptical about claims that are made too soon, too casually, and frankly, without evidence. And finally, what I would say with regard to this issue, while neuroscience promises to open a whole new window on dyslexia and many other challenges that children can face, right now, much of what we know about dyslexia comes from the careful work of many, many people over many years, showing the importance of phonological ability and the importance of early environment, stimulative language, proper instruction in how to read. Reading can be mistaught. It's very easy to create what are called curriculum casualties, where you do not appreciate how reading is built and what should be reinforced. Emphasizing phonological skills, phonics, alphabetic principle, vocabulary, these are things that have been recommended by the National Reading Panel that are healthy and important. Currently, brain science doesn't add much to that, but it offers a promise that we can begin to understand differences between people that are very subtle and yet very profound. If dyslexia is ultimately rooted in a genetic wiring, a gene-brain difference, then it should occur in all written languages, not just in English. The question is, does it? And the answer is yes. Now, we do work where we study cognitive development and brain development in many languages using identical procedures. These are part of our NIH-funded studies that are looking at reading. And one of the things we find is that there are languages, for example, Spanish, which is much more what's called regular in the way spelling and sound is linked. So to put it simply, if you know how it looks in Spanish, you know how it sounds. It's an easier language to decode in many ways. English is more complex. There are words like M-I-L-L, and it's pronounced mill, and there's no problem. But there are words like P-I-N-T or pint, which by rule should be pint, but are pint because of morphological history and accidents of how English is developed. So English has a more complicated relation between how letters and sounds go together. It's called a one-to-many mapping. Well, the point is that if you look at the tendency for dyslexic children to make errors, you will find, by whatever criteria you use, 5 to 10% children in English making the kinds of errors that we diagnose as dyslexia, particularly pseudo-word reading, sounding out novel words. If you look in the Spanish population where it's easier to decode, you might not see those errors. And so you might think dyslexia doesn't exist, but, and this is important, the other features of dyslexia are that decoding words takes your whole soul to pull off the page. It's slow, labored, and as well as error-prone. And when we look at the fluency of decoding, we find similar proportions of children in all languages who are not becoming automatic, who are struggling with decoding, which makes comprehension for written language difficult. So while dyslexia might present in slightly different ways in terms of tests, the underlying problems of becoming an automatic decoder or fluent reader are in fact universal. There have also been some important brain imaging studies, since this is my field, that show that we find differences in those left hemisphere circuits that I was talking about that are not only seen in English, but are seen in Spanish and other world languages, and even languages like Chinese that have a very different form. So there appears to be a universality in the problems of learning to become a fluent reader that are not specific to English and therefore require a global perspective. Literacy is extremely important in a modern world, and it is particularly important in the developing world where many languages are spoken. Some of the work that I do through my work at the National Institutes of Health is involved in looking at the developing world and literacy rates and connections to early preschool experiences. And I think it's very important for us to understand that problems with reading are not only profound when they happen, but they are universal and global in their manifestation.